Welcome to Lame Boys RC. My name is Werner. So over the last year we spent a lot of our spare time building our own transmitter electronics and firmware. It started when we got interested in airplanes, but we didn't have a stick transmitter. We had this old simulator lying around, so we thought, hey, why not convert that one and make it a fully functional RC transmitter? I mean, how hard can it be? Turns out not that hard, but takes a lot of time. A few months later, we acquired a couple of vintage car transmitters from eBay, and in the process of the last year, we also converted them to 2.4 gigahertz to make it work with our existing cars. Now our requirements were that we want to have all the modern functions that we are so accustomed to with the modern radios. We wanted to be 2.4 gigahertz for reliability and range. It needed to be compatible with our existing receivers in the cars, since we have already so many of them. We wanted support multiple models, even though the old transmitters are clearly not designed to do that. We wanted convenience functions like endpoint adjustments, expo, advanced mixing options, and so on. All the stuff that we know and love today. Now in modern transmitters, you have display and buttons to perform all these advanced operations. Of course, we could have added a display and buttons to each of the transmitters, but that's a lot of work, and it's not so easy where to put them sometimes, and making them mount nicely and look great is a lot of work. And also, do you really want to cut up beautiful transmitters like the old Electronics, or very special ones like the American Joe Mac? That while it looks very toyish, it's still almost like a piece of history. So we wanted to keep them as original as possible. So in order to work around that, what we decided is, hey, why not use the smartphone? We have that with us anyway. And why not just use it to change settings on the transmitters? Now, the smartphone obviously doesn't come with radio electronics that is compatible with the proprietary systems in the transmitters. So in order to overcome that, we made a bridge device. This bridge device has a Wi-Fi access point built in, and also the proprietary radio, and this allows us to configure the transmitters with a smartphone app that we made. Let me show how that works. So when we want to adjust the settings on the transmitter, we power up the bridge device. We then launch the application and connect the Wi-Fi of the phone to the bridge. We can then click on the connect button, and it scans for transmitters. When the transmitter is on, it appears in the list here. The transmitter is right now operational. It's controlling here the MO5. I can connect to it, and here we can adjust the settings. For example, we can go into the mixer settings, and for the steering, we adjust the subtrim. And as you can see, that's reacting live onto the car. And the settings are stored in the transmitter, as well as in the smartphone. We can also change the model. So we connect to the transmitter, and then from the menu, we change model. We have a list of all the models that we have stored on the phone. We select the buggy, the Durga. It has loaded, and now the same transmitter is controlling the buggy. When we are done, we disconnect from the transmitter, we shut everything down, and we can just drive. It's as simple as that. A modern smartphone has virtually unlimited memory, so we can easily install the configuration for a whole fleet of vehicles on it without any problems. The configuration application is actually a progressive web app which means you can simply start it in the browser, laneboysrc.github.io/rc headless transmitters. Link is in the video description. And from there on, you can install it from the menu of the browser at your home screen, just like any other app. Being a web app means you can not only use it on the phone or tablet, but you can also use it on your PC or Mac. The app has been tested on Firefox and on Chrome, and on Android it works really well in the offline mode that the Chrome provides. If we look at different transmitters, we find that they all have different ways to control things. On the stick transmitter, for example, we find mechanical trims that move the potentiometers inside. On that JOMAC transmitter, the throttle is designed for gas engines, so it basically only has forward movement. And the steering trim is an extra potentiometer. On the Atronics, the throttle goes into both directions, forward and backwards. And all the controls are individual potentiometers, including the trims. We therefore separated the transmitter configuration from the model configuration. So for example, when we use the JOMAC transmitter, then the car can only drive forward, but it uses the full range of the potentiometer. If we use the Atronics transmitter, the same car model configuration has access to both forward and reverse controls. So let's have a look now at all the components involved to build one of these transmitters. The transmitter is based on the STM32F103 microcontroller here. You can purchase these modules cheaply on eBay and AliExpress. They are less than $2 including shipping. The Hobby King system is based on the NRF24L01. So we're using here a module that has the chip plus a power amplifier. Again, we're talking less than $3 from China for this kind of thing. They even come with an antenna, and they perform in our tests as good as the Hobby King transmitters. The software is prepared to support RF protocols other than the Hobby King one, but currently only the Hobby King protocol is implemented. Quite a while ago we made receivers, which you can find also on our GitHub account and on our blog. I will put a link to them in the description. So you can basically build your whole end-to-end RC system. The transmitter has in total 9 analog inputs and 8 digital inputs. And you can use the analog inputs for potentiometers, and the digital inputs can be used for switches. You can combine multiple digital inputs into a multi-position switch if requested, and each of the inputs, analog or digital, can be assigned to a logical function like steering or throttle or aileron. So then when you load your RC model, for example a car, then the model can query what's the value for steering, and the transmitter can figure out which of the inputs is connected to the label steering and return the proper value regardless of how it's wired up. You only need to configure it once when you build a transmitter. The transmitter is powered from a single lithium-ion cell. We scavenged those from an electronic toothbrush. This particular one has about 800 milliampere hours at 3.7 volts. And it can easily power the transmitter for more than 12 hours. The battery is protected and charged through another module from China. It is this TP4056 module. Again, this costs less than $1 including shipping, and it works very well both to protect the lithium-ion battery as well as charge it. Wiring the transmitter is straightforward. Every of the transmitters we built so far had a little bit of a different layout, so far we did not bother making a circuit board, but we just used a Vera board to build everything up in the way that we needed. So in the stick transmitter, the wireless module is directly mounted at the antenna output, and with a cable running to the MCU. The MCU is on a breadboard, and the lithium battery as well as the charger module are on a 3D printed mount. For the JOMAC transmitter, we created a 3D printed base that looks somewhat like that. There is a slot here that holds a lithium battery, a flat style in this case, and a tiny antenna to easily fit inside the case. We are not worried so much about range or performance since we're only using this with cars. This has also the advantage that the antenna is inside the case, so from the outside you can never tell that this is a 2.4 gigahertz conversion. We only performed the absolute necessary minimum changes to the transmitter. So we removed a few components from their traces. We kept all the original wiring and just added a few extra wires, but it is very easy to convert this rare piece of history back into original condition. The circuit board and all the other stuff has basically untouched. The modifications on the Atronics transmitter were a little bit more substantial. We removed all the original wiring harness because it was quite messy and large, since there are so many potentiometers and so many functions inside. We printed a frame on our 3D printer that houses the modules. The RF module is here mounted on top of the MCU board and also has a holder for the battery here, plus the charger board and the buzzer mounted here. And all this assembly sits inside the existing battery tray and did not require any mechanical modifications to the transmitters. The MCU is also driving with a PWM output the analog battery meter, so we can see the battery state just like in the old days by looking at the needle moving. The bridge is built on top of an Orange Pi Zero, which is a single board computer similar like a Raspberry Pi, but less powerful. It's more like the Raspberry Pi 2, and it's therefore also much smaller, which is beneficial in application, especially since we don't need things like HDMI output for this application. It has built-in Wi-Fi, which we certainly need, with a tiny antenna. We added a small circuit board on the pin headers with an NRF 51822 chip that is compatible with the NRF 24LO01 that is in our transmitters, and a power button to reliably switch the system off. The Orange Pi runs Linux, so with the custom software provided as part of a project, the configurator web app can control the transmitters. So in case you fancy to build your own system, Hardware and Software publishes an open source project on our GitHub account. We put the links in the video descriptions. But a word of warning though, it takes quite some effort to build up such a system. Considering the fact that today you can buy a very inexpensive radio system for less than $40 that has all the same functions, you have to have a very good reason why you want to spend all this effort. Converting a vintage transmitter is certainly one. Another one would be if you would require custom controls for a vehicle. Or if you just enjoy building things. It's always satisfying to make something work. In case you're interested in DIY electronics, I also highly recommend the fantastic community at RC Groups. There you can find all kinds of open source RC hardware and software projects. For example, there is a similar project converting old transmitters to 2.4 gigahertz, which has a different approach. They are basically making a module that reuses all the low frequency electronics and outputs the PPM signal into a 2.4 gigahertz RF module to broadcast to a modern receiver. I will also put links to those kind of projects in the video description. So thanks for watching. Please like and subscribe, and see you next time. Bye.